Hello, good evening, friends. So, going to start again a very important research paper on robot-driven calibration and accuracy assessment of MetaQuest 3 inside-out tracking using a TECHMAN TM5-900. Okay, collaborative robot. So, going to start it. First, I will do screen large. Now, going to play it.
Article: Robot-driven calibration and accuracy assessment of MetaQuest 3 inside-out tracking using a TECHMAN TM5-900 collaborative robot. Josep Lopez Zarbao, Marco Antonio Rodriguez Fernandez, Marcos Fondes Zanui, Jordi Calvo Sanz, and Juan Jose Garcia Tirado. Technocampus, Universitat Pompeu Fabra, 08302.
Starting from here.
Abstract. We present a systematic evaluation of the positional and rotational tracking accuracy of the MetaQuest 3 mixed reality headset using a TECHMAN TM5-900 collaborative robot as a highly repeatable robot-driven reference. The headset was rigidly attached to the robot's tool flange and subjected to single-axis translational motions and rotational motions. Each test was repeated 3 times, and the resulting trajectories were averaged to improve statistical robustness. Both data sources were integrated into a single Python-based application running on the same computer. The headset streamed its data via UDP, while the robot, implemented as an ROS2 node, published its data to the same host. This configuration enabled simultaneous acquisition of both streams, ensuring temporal consistency without the need for offline interpolation. All comparisons were performed in a relative reference frame, thereby avoiding the need for absolute hand-eye calibration. Coordinate frame alignment was achieved using singular value decomposition-based rigid body procrusts analysis. Over 2,848 synchronized samples spanning 148 synchronized samples achieved a mean translational RMSE achieved a mean translation coefficients greater than 0.99 on all axes. These results show sub-millimeter positional tracking and sub-degree rotational tracking under controlled conditions, supporting the potential of the MetaQuest 3 precision-oriented mixed reality applications in industrial and research settings. Keywords: mixed reality, inside-out tracking, rigid spatial alignment, tracking accuracy, collaborative robot, metrology, healthcare, procrusts alignment. Academic editor, Francesco Agugeri received, the 6th of March 2026 revised, the 1st of April
It is a
2026
really
revised,
current paper.
the 7th of April 2026 published, the 8th
You can see. So, it's published on 8th of April 2026. It's very new paper of this year only. Okay.
of April 2026 Copyright terms and conditions of the Creative Commons Attribution License.
Introduction.
1. Introduction.
Yeah.
In recent years, immersive virtual reality head-mounted displays have attracted increasing interest in physiotherapy and rehabilitation, not only as tools for therapeutic intervention, but also as potential instruments for the objective assessment of human movement. Beyond their role as training interfaces, several studies have investigated the validity of integrated HMD tracking systems for quantifying clinically relevant variables such as head kinematics, postural control, and balance. From a clinical perspective, the interest in these technologies lies in their capacity to provide objective, repeatable, and low-cost measurements of functions that have traditionally been assessed using manual instruments or observational tests. Within the musculoskeletal domain, and specifically in the cervical region, recent studies have evaluated standalone HMDs for estimating cervical range of motion and performing sensor-motor function tests. These studies report errors comparable to clinical instruments and good intra-session repeatability, supporting the potential of HMDs for functional screening and monitoring in clinical settings. In parallel, immersive VR has been explored in vestibular physiotherapy for patients with dizziness or gaze control disorders. Furthermore, the integration of eye tracking systems into modern headsets has opened new possibilities for assessing oculomotor function and vestibulo-ocular reflex gain. Despite these advances, the existing literature tends to address these functional components in a fragmented manner. Few studies have validated integrated HMD-based assessment protocols against well-characterized external references. A critical prerequisite for these clinical applications is the rigorous characterization of spatiotemporal tracking accuracy. Reproducible evaluation protocols that distinguish systematic errors from intrinsic dynamic variability are necessary for the correct interpretation of measurements. Commodity VR headsets, such as the MetaQuest 3, have rapidly evolved into compact platforms that provide real-time 6-degree of freedom head pose estimates through inside-out tracking. Such pose estimates are increasingly exploited as a general-purpose motion sensing modality because they are easy to deploy and do not require external cameras. However, the achievable accuracy of inside-out tracking is not guaranteed a priori. It depends on the headset hardware, the proprietary tracking pipeline, the visual features available in the environment, and motion dynamics. For applications where millimeter-level translation errors or degree-level orientation errors may impact downstream analysis, such as the clinical assessment of cervical ROM, a rigorous calibration methodology is required. A common strategy to characterize tracking performance is to compare the HMD pose stream against an external reference sensor. While effective, these approaches either require specialized infrastructure or introduce their own placement issues. In contrast, industrial robots and collaborative manipulators provide highly repeatable motion generation, making them an attractive reference platform for evaluating VR tracking under controlled trajectories. Nevertheless, accurate validation requires rigorous spatiotemporal alignment. Neglecting internal clock drift or assuming fixed delays can lead to overestimation of dynamic tracking errors. Recent advances in generalized and multi-camera relative pose estimation further contextualize the present study within the broader problem of robust spatial registration. In particular, minimal and closed-form solvers for generalized camera systems have shown that reliable pose recovery can be achieved even in non-central imaging configurations and with reduced correspondence sets, including formulations based on 6-point correspondences and affine correspondences. Although these methods address a different estimation setting than the robot-driven headset benchmarking considered here, they are relevant because they illustrate how future validation protocols could be extended toward richer sensing configurations, multi-camera headset models, and more visually challenging environments while preserving geometric rigor. The scope of this work is intentionally metrological, to characterize the intrinsic tracking precision of the MetaQuest 3 under controlled and reproducible conditions. Performance under dynamic, multi-axis, or visually degraded conditions is an important complementary objective, but it lies outside the scope of the present study. Accordingly, this paper presents a robot-driven calibration and accuracy assessment of the MetaQuest 3 headset using a TECHMAN TM5-900 collaborative robot as a motion reference. Unlike studies aimed primarily at clinical or biomechanical inference, the goal here is to quantify how closely the 6 DOF pose reported by the headset matches a repeatable reference trajectory in both translation and rotation, while providing a transparent processing pipeline that can be reproduced and adapted to similar setups. The main contribution of this work is therefore not the introduction of a fundamentally new validation paradigm, but the implementation and systematic validation of a practical, reproducible, and robot-referenced benchmarking pipeline from MetaQuest 3 tracking under controlled 6 DOF trajectories. The main contributions of this work: a practical experimental setup in which the MetaQuest 3 is rigidly mounted to the end effector of a TECHMAN TM5-900 cobot, enabling controlled and repeatable 6 DOF trajectories. A spatial preprocessing pipeline that rigidly aligns the robot and headset coordinate frames and ensures consistent angle handling across both pose streams. A comprehensive set of translational and rotational accuracy metrics, reported per axis and in 3D, together with representative error distributions over the tested workspace and motion profiles. 1, 2, 3.
Yeah.
The remainder of the paper is organized as follows. Section 2 describes the experimental platform, acquisition pipeline, coordinate alignment procedure, and error metrics.
Yeah.
Section 3 presents the translational, rotational,
Rotational,
cross-axis, and spectral
and
results.
spectral results. And
Section 4
section
discusses
4.
the implications of the findings and their practical relevance.
Yeah.
Section 5 summarizes the main limitations and outlines future research directions. Finally, Section 6 concludes the paper and provides recommendations for extending robot-based evaluation protocols for VR inside-out tracking.
Yeah.
Materials and Methods 2.1. Experimental Setup 2.1.1. The TM5-900 is a 6-axis collaborative robot with a 900 mm reach, 4 kg payload, and a certified repeatability of plus or minus. Its high repeatability makes it a reliable reference for controlled tracking evaluation. MetaQuest 3 HMD. The MetaQuest 3 employs ViSLAM tracking using 6 cameras and a high-rate IMU. As shown in Figure 1, the headset was rigidly mounted to the robot's tool flange using a custom 3D printed bracket, ensuring no relative motion between the headset and the robot's tool center point. Throughout all data acquisitions, the measurement conditions were kept stable. The ambient illumination was monitored with a lux meter and maintained between 400 and 500 lux, and the visual scene remained unchanged for all trials. Position and orientation data from both the robot node and the MetaQuest 3 application streaming quaternion-based poses over UDP. Each CSV file contains timestamp T, MetaQuest 3 columns, position and quaternion. Robot columns, Cartesian position and Euler angles. Figure 1. Experimental setup showing the MetaQuest 3 head-mounted display rigidly attached to the end effector of the TECHMAN TM5-900 collaborative robot via a custom 3D printed bracket. To improve measurement reliability, each single-axis test was repeated 3 times under identical conditions. The 3 recorded trajectories for each degree of freedom were then sample-wise averaged, and all subsequent alignment and error analyses were performed on these averaged trajectories. This averaging strategy reduces the influence of random per-run noise while preserving the deterministic motion profile imposed by the robot. Both the robot and the MetaQuest 3 stream data to the same host computer, sharing a common system clock. Both the robot and the MetaQuest 3% operate at a synchronite of 20%. The robot exposes joint states and the Cartesian pose through the ROS2 topic interface, while the headset transmits 6 DF pose data via UDP. Timestamps are assigned at the receiving application level using the host system clock time.perf, ensuring a shared time reference. The trials were conducted within the robot's operational envelope, with maximum end effector translation and rotation speeds limited to 40 mm per second and 11 degrees per second. Tracking origin and repeatability. The coordinate system was defined relative to the virtual world origin. At the beginning of each run, the tracking origin was reset using the OpenXR set tracking origin function to reduce run-to-run variability. Robot reference quality. In this work, the collaborative robot is used as a repeatable motion reference to generate controlled 6D of trajectories. It is important to distinguish repeatability from absolute accuracy. While collaborative manipulators typically provide highly repeatable motion, the absolute end effector pose obtained from forward kinematics can still be affected by residual kinematic parameter errors, tool center point definition errors, joint compliance, and mounting deflections. Consequently, the TM5-900 serves here as a controlled motion generator and reference trajectory source, rather than a traceable absolute metrology instrument. The reported residuals therefore quantify agreement between the headset and the robot-driven reference, and should not be interpreted as a full decomposition of headset-only error in a traceable common frame. Accordingly, the robot should be interpreted here primarily as a deterministic trajectory generator that enables consistent replayable motions, rather than as a traceable metrology-grade reference. This distinction is relevant when interpreting the error metrics reported in Section 205. In particular, the reported error metrics intentionally include any systematic offsets that may arise from fixed mounting geometry and coordinate frame mismatch between the robot reference and the headset tracking frame. For completeness, the dominant contributors to the reference uncertainty in this setup are robot motion repeatability and servo variability, TCP and tool frame definition errors, compliance and micro deflections under gravity and acceleration, and numerical resolution quantization of the robot pose stream, and residual temporal misalignment. A compact expression for the aggregated reference contribution can be written as, where each term represents, respectively, repeatability, TCP mount definition, compliance deflection, numerical logging resolution, and time alignment uncertainty. To provide a quantitative bound on the reference uncertainty, the dominant contributors were estimated as follows. The robot's certified repeatability represents the most precisely characterized term. TCP and mounting uncertainty, arising from the custom 3D printed bracket, were estimated geometrically at less than 0.5 millimeters. Compliance-induced deflections under the applied quasi-static loading conditions were estimated at less than 0.1 millimeters, consistent with values reported for similar lightweight cobots. Numerical logging resolution contributes less than 0.01 millimeters. Temporal misalignment uncertainty is quantified in the section temporal synchronization and timing uncertainty. Combining these contributions in quadrature yields an aggregate reference uncertainty bound of approximately 0.55 millimeters, which should be borne in mind when interpreting the 3D RMSE of 0.621 millimeters reported in Section 3. Therefore, the reported results should be regarded as a benchmark of headset pose accuracy against a highly repeatable robot-driven reference. For applications requiring absolute pose agreement in a common coordinate frame, an additional spatial registration step should be incorporated, and its uncertainty reported. Temporal synchronization and timing uncertainty. The principal sources of residual timing uncertainty are ROS2 DDS message, scheduling jitter, and UDP network, stack buffering for the MetaQuest 3 stream. Combining these in quadrature yields a timing uncertainty of U time less than 5 milliseconds. At the nominal translational speed of 40 millimeters per second, this corresponds to a worst-case positional error contribution of 0.2 millimeters, which constitutes U time in equation. Reference trajectories. The robot executed a sequence of piecewise linear trajectories along the 3 Cartesian axes and along the 3 rotational duefs. Each duef was actuated individually with a go and return motion about the pose. Translations exhibited a peak excursion of approximately 200 millimeters, while orientations followed analogous ramps spanning from minus 65 degrees around the x-axis and from minus 85 degrees around the x-axis. All trajectories were executed using a trapezoidal velocity profile, with a nominal translational speed of 40 millimeters per second and a maximum translational acceleration of 100 millimeters per second squared. These motion parameters were selected to keep the dynamics within a moderate range while still exciting the headset tracking pipeline with non-negligible velocities and accelerations. The motion commands were defined in the robot tool reference frame rigidly attached to the headset mount, with the frame origin located at the selected TCP associated with the fixture. The positive X, Y, and Z directions used for the translational tests, and the corresponding rotations about those axes, are now indicated in Figure 1 and described in the text for clarity. Translational tests were executed at 40 millimeters per second, and a maximum translational acceleration of 100 millimeters per second squared, whereas rotational tests were executed at 11 degrees per second, and a maximum rotational acceleration of 40 degrees per second squared. The robot was initialized from a nominal configuration selected within a regular region of the workspace, away from kinematic singularities, and the commanded trajectories were designed so that singular configurations were not approached during the experiments. Prior to physical execution, all planned trajectories were validated in simulation using the ROS2 framework. The robot model was visualized in RVs, and the motions were executed in Gazebo to verify that every target pose lay within the robot's reachable workspace, and that no joint limit violations, singularities, or self-collisions occurred. This pre-validation step ensured that the commanded trajectories were kinematically feasible given the physical constraints of the TM5-900. This force motion enables a direct comparison between the reference robot trajectories and the positions orientations reported by the headset under repeatable conditions. 2.2. Relative Coordinate Framework. Let n denote the total number of synchronized samples used in the analysis. The robot and headset trajectories, as ordered point sets, and 9091, respectively, denote the corresponding pose samples at index I after synchronization. The matrices Q and R denote the stacked point coordinates used in the rigid alignment step. In the error analysis stage Q, the headset-derived quantity at sample I and R, the corresponding robot reference value at the same sample. To avoid the complexities of absolute hand-eye calibration, all analyses are performed in relative coordinates. Given a trajectory p equal to, the relative displacement at sample k is defined as. This removes any constant offset between coordinate frames and isolates the motion component. 2001, 10n 20 million and 200 linear movement robot. 200 linear movement. Y linear movement 100 times 200. Linear and rotational threes used for calibration. Corresponding measurements reported by the MetaQuest headset. SVD-based rigid body alignment, efferent coordinate systems. To align them, we compute an optimal rigid body transformation using SVD-based per crest analysis. Given n corresponding pairs. 1. Cross-covariance matrix. 3. Singular value decomposition. Optimal rotation equal to +1. The transformed MetaQuest 3 positions are then. The MetaQuest reports orientation as unit quaternions, which are converted to Euler angles using the SciPy.spatial transform. Rotation library, with the XYZ intrinsic convention, is applied to handle plus or minus 180 degrees discontinuities, which are critical for the yaw tests near wrapping boundaries. The XYZ intrinsic convention was selected to match the Euler angle representation used by the TM robot controller, which reports orientations using the static XYZ convention. Consistency was verified by confirming that, for single-axis rotational tests, the reported robot Euler angle on the active axis was monotonically consistent with the headset angle after per-crust alignment, with cross-axis angles remaining near 0. 2.5. Error metrics. 4 complementary metrics are used to characterize tracking accuracy: root mean square error, mean absolute error, maximum absolute error. Pearson correlation coefficient, percentile errors. RMSE emphasizes larger errors, while May is more robust to outliers. Max error captures worst-case performance, and Pearson's R quantifies trajectory shape fidelity independently of scale. Percentile-based metrics P and P as the 95th and 99th percentiles of the absolute error values. Results. Translational tracking accuracy. The per-axis and aggregate translational error metrics. The MetaQuest 3 achieved sub-millimeter RMSE on all 3 axes, with the z-axis showing the lowest error and x the highest. The 3D Euclidean RMSE combining all 3 axes was 0.621 millimeters.
0.621 millimeters.
Table 2. Translational tracking error metrics. Figure 3 shows the overlaid translational trajectories and the temporal evolution of translational errors on each axis. Errors remain bounded within 1 millimeter throughout all tests, with no systematic drift. The robot and MetaQuest 3 traces are virtually indistinguishable, confirming the high correlation values. Figure 3. Temporal evolution and linear position error of the robot and effector position, and the MetaQuest 3 headset position along the 3 Cartesian axes. Figure 4 shows the residual translational errors on each axis. The error distributions are approximately centered at 0, confirming the absence of systematic bias after the per-crust alignment. Figure 4. Histogram of the axis-wise translation error after a fine temporal alignment, axis mapping, and frame rotation alignment. 3.2. Spectral error analysis. To characterize the frequency content of the translational tracking residuals, the power spectral density of the per-axis translation error was estimated using Welch's method for the x, y, and z axes. The resulting spectra, shown in Figure 5, exhibit no narrowband peaks or dominant resonance lines within the analyzed 0 to 10 h the range, indicating that the residual error is not driven by a single periodic disturbance or mechanical vibration. On the x-axis, the PSD shows a rapid decay from very low frequencies, and then remains within a relatively narrow band over the rest of the spectrum, without pronounced tonal components. The y-axis presents a slightly more marked elevation of power at very low frequencies, suggesting the presence of slow-varying components, such as minor 6-slam estimation drift or quasi-static deflections in the robot headset assembly. The z-axis PSD exhibits a broadband profile broadly consistent with that of the x-axis, with a moderate low-frequency elevation below 1 Hz but no identifiable resonance peaks. The relatively lower absolute power level on the z-axis, compared to y, is consistent with the lower translational RMSE observed on that axis, confirming that the z-tracking pipeline introduces marginally less drift or quasi-static estimation error under the tested vertical translation trajectory.
That's good.
Cont. Power spectral density of the translational tracking error along the x, y, and z axes, estimated using Welch's method. In all cases, the absolute power levels remain compatible with the sub-millimeter RMSE values reported in Table 2, supporting the interpretation that the dominant error sources behave as broadband noise, with a limited low-frequency structure rather than as strong oscillatory artifacts. 3D translational trajectories. Spatial trajectories for all 3 translational tests. The close overlap between the robot and MetaQuest 3 paths in 3D space confirms that the SVD-based alignment successfully transforms the MetaQuest coordinate frame to the robot frame. 3.4. Rotational tracking accuracy. Table 3 summarizes the rotational error metrics. The pitch axis showed the lowest RMSE, while yaw exhibited the highest. This is consistent with the larger angular range of the yaw test and the known sensitivity of VSLAM to rotations around the vertical axis. Table 3. Rotational tracking error metrics. Trajectories in 3D space. Trajectories in 3D space. 150 trillion, 150 trillion, 150 trillion. 307.5. 299.4. 199, 299. 199. 199, 2. 200.2. 200.4. 200.4. 200.3 aligned trajectory. So the rotational trajectories and the temporal rotational errors for each axis. As with translation, the robot 200.4. 200.4. So the rotational trajectories and the temporal rotational errors for each axis. As with translation, the robot and MetaQuest 3 curves are nearly indistinguishable. Figure 8 shows the residual rotational errors on each axis. The distributions are approximately symmetric and centered at 0, with the yaw axis exhibiting the widest spread, consistent with its higher RMSE.
Yeah.
Figure 7. Rotational trajectories and rotational error for roll, pitch, and yaw axes. Figure 8. Histogram of the axis-wise rotation error. 3.5. Cross-axis coupling. Table quantifies the cross-axis translational error observed during single-axis movements. During a movement along axis 1, the RMSE on the two perpendicular axes J and K reflects unintended crosstalk. Values range from 0.04 mm to 0.071 mm, and confirming that the SVD-based alignment effectively decouples the three Cartesian axes. In addition to translational crosstalk, rotational cross-axis coupling was quantified for each single-axis rotational test by computing the RMSE of the two non-commanded Euler angle residuals. Specifically, during the RX test, crosstalk was evaluated on pitch and yaw, during the RY test on roll and yaw, and during the RZ test on roll and pitch. The resulting values, summarized in Table 5, remain small relative to the commanded angular excursion, indicating limited rotational crosstalk after frame alignment, Euler angle unwrapping, and axis normalization. Table 4. Cross-axis translational RMSE during single-axis tests. Table 5. Cross-axis rotational RMSE during single-axis tests. 4. Discussion. The results show that the MetaQuest 3 can reproduce robot-driven translational trajectories with sub-millimeter accuracy, and rotational trajectories with sub-degree accuracy under well-defined test conditions. Translational RMSE remained below 0.5 mm on all axes, with a 3D Euclidean RMSE of 0.621 mm, while rotational RMSE remained below 0.4 degrees on all axes, despite the relatively large angular excursions tested.
Yeah.
The very high Pearson correlation coefficients further indicate that the headset preserves the temporal structure of the robot trajectories with no observable systematic drift or lag. Repeating each test 3 times and averaging the resulting trajectories also strengthens confidence in the reported values by reducing run-to-run variability. From an application-oriented perspective, this level of tracking accuracy is relevant not only in metrological terms, but also in relation to user comfort and safety. Mismatches between visual feedback and head motion, including tracking error and jitter, are well-known contributors to visually induced motion sickness, which can negatively affect rehabilitation adherence, particularly in vestibular populations.
Yeah.
The observed error magnitudes are also small relative to the movement ranges typically considered in cervical and vestibular assessments. Cervical range of motion measurements are usually on the order of several tens of degrees, and conventional clinical tools often exhibit standard errors of measurement in the range of 3 degrees to 5 degrees. In this context, the rotational errors observed here are substantially smaller than those clinical uncertainty ranges. These findings therefore support the potential of the MetaQuest 3 as a quantitative sensing platform for controlled rehabilitation-oriented applications, although dedicated clinical validation remains necessary before broader diagnostic use can be assumed. Table 6 places the present results in the context of representative prior studies. The translational RMSE reported here is substantially lower than the 3.19 mm reported by Benash-Sheikh et al. For the Quest 2, using realistic head trajectories on a UR5V robot. This difference is expected. The present protocol uses slow, single-axis, piecewise linear motion specifically designed for controlled metrological characterization, rather than naturalistic head motion. Accordingly, the present results should be interpreted as a best-case benchmark under well-defined laboratory conditions, whereas the results of Benash-Sheikh et al. Reflect performance under more dynamic, multi-axis, and ecologically valid conditions. Compared with optical motion capture-based validation frameworks, the proposed protocol prioritizes reproducibility, reduced infrastructure requirements, and a unified acquisition chain.
Yeah.
Unlike hand-eye calibration methods, which aim at absolute extrinsic registration between sensing and robot frames, the present study only requires rigid alignment for relative trajectory comparison after removal of constant offsets. For this reason, an SVD-based per crust solution was adopted, as it provides a closed-form least squares estimate with well-established numerical stability for corresponding 3D point sets. By moving both streams to a common origin before alignment, the number of calibration unknowns is reduced while preserving a rigorous comparison framework. This choice is also consistent with previous sensor alignment literature. Table 6. Quantitative comparison with representative prior evaluations of VR-MR headset 6 DOF tracking accuracy. An important practical aspect of the present work is the tightly integrated acquisition pipeline, in which both the collaborative robot and the MetaQuest 3 stream their poses to a single Python application running on the same computer. This design reduces the need for offline clock drift estimation and temporal interpolation, thereby addressing a source of uncertainty that is often underemphasized in previous studies.
Yeah.
Combined with a relative coordinate framework and rigid body per crust alignment, this architecture makes the methodology easier to reproduce, while still enabling a rigorous comparison of translational and rotational tracking performance.
Sure.
The observed anisotropy in rotational accuracy, with larger errors around the vertical yaw axis, is also consistent with the known sensitivity of visual inertial SLAM pipelines to rotations that reduce the effective parallax of visual features. Even in this more challenging configuration, however, the MetaQuest 3 remained within a sub-degree error range and maintained excellent correlation with the robot reference. Likewise, cross-axis translational coupling remained below 0.08 mm RMSE during nominally single-axis motions, indicating negligible parasitic motion and limited crosstalk for the trajectories considered. The spectral analysis of the translational residuals supports the same interpretation. The estimated power spectral densities do not show dominant periodic components, suggesting that the residual discrepancies between the robot and the headset are not driven by strong oscillatory modes or mechanical resonances. Instead, the error behaves predominantly as low-amplitude broadband noise. The slightly elevated low-frequency content observed on the Y and Z axes suggests the presence of slow-varying estimation effects within the MetaQuest 3 ViSLAM pipeline, but these variations remain well within the sub-millimeter error envelope measured in this study. 5. Limitations. While the proposed robot-driven evaluation protocol provides a controlled and highly repeatable environment to characterize the MetaQuest 3 tracking performance, several limitations must be acknowledged. First, the TECHMAN TM5-900 collaborative robot is used as a repeatable trajectory generator, rather than as a fully traceable metrology grade reference. Consequently, the reported error statistics include robot-related uncertainty contributions already discussed in section 2.1.4, which are not independently identified or compensated in the present work. Second, all analyses are performed in a relative coordinate framework, with errors computed after rigid per crusts alignment between the robot and headset pose streams.
Yeah.
This design deliberately avoids the need for absolute hand-eye calibration and makes the protocol easier to reproduce. But it also means that constant spatial offsets and residual frame misregistration are not explicitly quantified. So the metrics primarily reflect repeatability rather than absolute pose agreement.
Yeah.
Third, the experimental protocol focuses on single-axis, piecewise linear trajectories with moderate velocities and accelerations under controlled setup. While the spectral analysis suggests that residual errors are mainly broadband in nature, the observed sub-millimeter translational and sub-degree rotational errors still characterize a best-case scenario. Performance in more demanding settings, such as highly dynamic motions, complex multi-axis paths, cluttered environments, or degraded visual texture and lighting remains outside the scope of this study and may exhibit larger errors. Fourth, the evaluation considers a single headset unit, a single robot platform, and a specific mechanical mounting configuration. Device-to-device variability, alternative mounting geometries, and other robot types are not explored. In particular, the custom 3D printed bracket is assumed to be rigid, but small unmodeled flex or play could contribute to the overall error budget. Fifth, because the experiments were conducted in a stable laboratory scene with controlled illumination and static visual features, the reported metrics should be interpreted as a reproducible benchmark under well-defined operating conditions. Further experiments in visually degraded, cluttered, or dynamic environments would help assess the robustness of the tracking pipeline under a broader range of application scenarios. Finally, the processing pipeline relies on a unified acquisition architecture in which both the robot and the headset stream data to the same computer. This design reduces temporal misalignment compared to independently logged streams, but residual timing uncertainty due to communication delays, buffering, and software scheduling cannot be fully excluded and is not separately quantified in the reported metrics. Conclusions. This work presented a robot-driven protocol for quantifying the 6 DOF tracking accuracy of the MetaQuest 3 mixed reality headset using a TECHMAN TM5-900 collaborative robot as a highly repeatable motion reference. By rigidly mounting the headset to the robot, streaming both pose sources into a unified acquisition pipeline, and aligning their coordinate frames through SVD-based rigid body per crusts analysis, the proposed methodology enables a transparent and reproducible benchmark under controlled conditions. To improve statistical reliability, all trajectories were pre-validated in simulation and repeated multiple times. Under the tested single-axis trajectories, the MetaQuest 3 achieved a 3D Euclidean, translational RMS 6, 21 mm, and a mean rotation coefficients, with Pearson correlation coefficients graders. Negligible and no systematic drift was observed during the tests. These results indicate that, relative to the highly repeatable robot-driven reference used here, the MetaQuest 3 provides a level of tracking precision that is promising for applications requiring accurate pose estimation under controlled laboratory conditions. The present findings establish a reproducible benchmark for the tested setup, but they should be interpreted within the scope of the experimental design. The results were obtained using a single headset unit, one robot platform, one mounting configuration, and stable environmental conditions. Moreover, the study was intentionally designed around relative frame comparison rather than absolute hand-eye calibration. For this reason, application-specific validation remains necessary before the device can be adopted in clinical or industrial workflows with defined operational tolerances. Beyond the numerical results themselves, the proposed pipeline provides a practical framework for future headset benchmarking. Design choices such as relative frame analysis and rigid spatial alignment, without full absolute registration, simplify the metrological evaluation of mixed reality devices while preserving methodological rigor. Several directions for future work follow naturally from the present study. First, evaluating multiple MetaQuest 3 units under different lighting conditions and levels of visual feature richness would help characterize inter-device variability and the robustness of the tracking pipeline. Second, more complex, high acceleration, and multi-axis trajectories should be introduced to better approximate dynamic human motion. Third, the use of an external metrology grade reference, such as an optical motion capture system, would enable a more complete uncertainty analysis and help separate the error contributions of the robot, the headset, and the alignment process. For applications requiring common frame agreement, future studies should also include explicit absolute registration experiments, including estimation of the constant rigid transform between systems and, where appropriate, hand-eye calibration. In addition, the mechanical contribution of the mounting interface should be characterized in greater detail by comparing alternative mounting solutions and quantifying flex or play-induced errors. Finally, dedicated timing experiments should be carried out to isolate the contributions of communication delay, buffering, and software scheduling within the unified acquisition architecture. Additionally, although the present protocol deliberately avoids absolute hand-eye calibration by operating in a relative coordinate framework, future work should quantify the constant spatial offset between the robot TCP frame and the headset tracking frame, for example through a dedicated AXI-B type hand-eye calibration procedure, in order to extend the protocol to applications requiring absolute pose agreement. Residual temporal uncertainty, discussed in the section, temporal synchronization and timing uncertainty, could also be reduced in future implementations through hardware-level timestamp injection or PTP-based clock synchronization between the HMD streaming interface and the robot controller. Author contribution.
So I'm going to stop it. You can see the contribution, author contributions. You can. Okay, let me play it. This is also important.
Conceptualization, methodology, validation, advisory role, JCS,
And you can see all the author contribution. You can see funding. Okay, you can see data availability statement and conflicts of interest. You can see references. You can see a lot of references are given. So it's time to see some summary. What I can do, 1 second. Press F11 and have it.
Research overview and motivation.
Yeah, fine. Okay, let's start it.
Clinical context, virtual reality, research overview and motivation. Clinical context, virtual reality headsets like the MetaQuest 3 are increasingly evaluated for clinical tasks, such as cervical range of motion assessments and vestibular physiotherapy, because they offer low-cost, objective motion tracking. Problem statement. While internal 6 degree of freedom tracking is convenient, it often lacks rigorous characterization. Relying on proprietary inside-out tracking requires validation against high precision, repeatable external references to ensure data reliability. Study objectives. This research aimed to quantify the intrinsic tracking precision of the MetaQuest 3 by comparing its reported pose data against a highly repeatable collaborative robot under controlled, reproducible laboratory conditions. 2. Experimental methodology. Reference platform. Researchers utilized a TECHMAN TM5-900 collaborative robot as the motion reference, chosen for its high repeatability of plus or minus 0.05, minus or 0.05, was mounted to the robot's tool flange via a 3D printed bracket. All trials were conducted in a room with stable, controlled ambient lighting to minimize environmental noise in the visual inertial SLAM tracking pipeline.
Yeah.
Data synchronization. Both the robot and the headset shared a unified host clock, facilitating simultaneous data logging without requiring complex offline interpolation. Trajectory design: the robot executed piecewise linear, single-axis trajectories, covering 200 millimeters of translation and up to 85 degrees of rotation. All motions were pre-validated in simulation to ensure they remained within the robot's kinematic limits. Spatial alignment: to enable comparison, the researchers employed singular value decomposition-based procrusts analysis. This technique allowed for the rigid body alignment of the headset and robot coordinate frames, effectively isolating the relative motion and avoiding the need for full, complex, absolute hand-eye calibration. 3. Quantitative performance results. Translational accuracy: the headset demonstrated sub-millimeter precision. The 3D Euclidean root mean square error was 0.621 millimeters, with individual axes showing errors ranging between 0.261 millimeters and 0.478 millimeters. Rotational accuracy: rotational tracking was similarly precise, with sub-degree error performance. The mean rotational RMSE was 0.143 degree, with the yaw axis showing the highest error at 0.259 degree, likely due to the inherent sensitivity of SLAM pipelines to vertical axis rotations. Temporal consistency: Pearson correlation coefficients were recorded at greater than 0.9999 across all axes, indicating that the MetaQuest 3 tracks the temporal structure of the motion with extremely high fidelity and minimal lag. Error distribution: residual error analysis revealed that the device does not suffer from systematic drift or dominant oscillatory artifacts. Instead, error patterns behaved as low amplitude, broadband noise, confirming the tracking system's stability under controlled movement. 4. Implications and future directions. Clinical relevance: the observed errors, sub-millimeter translation and sub-degree rotation, are significantly lower than the standard clinical uncertainty ranges found in manual diagnostic tools. This positions the MetaQuest 3 as a viable tool for objective, repeatable clinical screening. Metrological limitations: the study acknowledges that the robot serves as a repeatable trajectory generator rather than a NIST traceable absolute reference. Thus, the metrics capture the agreement between systems, rather than an absolute decomposition of the headset's internal sensor error. Future research. Recommendations for future work include testing the device under more dynamic, multi-axis scenarios, incorporating external motion capture systems for more rigorous uncertainty analysis, and evaluating multiple headset units to assess inter-device variability. Reproducibility. The authors emphasize that their methodology, specifically the unified acquisition pipeline and relative coordinate procrusts alignment, provides a highly transparent and practical framework that other researchers can easily adapt to validate other VR MR hardware. This research demonstrates that the MetaQuest 3 provides highly accurate 6D OF tracking within controlled environments, meeting the necessary thresholds for precision-oriented research and rehabilitation applications. By utilizing a collaborative robot as a deterministic reference and implementing a robust spatial alignment pipeline, the study provides a replicable benchmark for assessing modern mixed reality sensing systems. The findings support the shift toward using consumer-grade VR hardware as high-fidelity motion tracking tools, provided their deployment is grounded in rigorous, evidence-based calibration protocols.
Nice. So a nice summary is provided by this Speechify AI. That's cool. So starting the, I think, lecture, small structure. Okay, going to build up this.
For years, immersive virtual reality headsets have captivated researchers in fields like physiotherapy and rehabilitation. They're not just seen as tools for therapeutic intervention, but also as potential instruments for the objective assessment of human movement. Clinically, there's a strong interest in these technologies because they offer objective, repeatable, and low-cost measurements of functions traditionally assessed using manual instruments or observational tests.
Now we
For
can
example, in the musculoskeletal domain, recent studies have evaluated standalone headsets for estimating cervical range of motion and performing sensory motor function tests. These studies report errors comparable to clinical instruments, showing promise for functional screening. Vestibular physiotherapy, which helps patients with dizziness or gaze control disorders, has also explored immersive VR. With eye tracking systems now integrated into modern headsets, new possibilities for assessing ocular motor function have emerged. However, despite these advances, the existing literature often addresses these functional components in a fragmented way. Few studies have rigorously validated integrated headset-based assessment protocols against well-characterized external references. A critical prerequisite for these clinical applications is the precise characterization of spatial temporal tracking accuracy. Commodity VR headsets like the Meta Quest 3 have rapidly evolved into compact platforms, providing real-time 6 degree of freedom, or 6 DOF, head pose estimates through a technology called inside-out tracking. This means the headset tracks its own position and orientation using its onboard cameras and sensors, without needing external cameras. But the achievable accuracy of this inside-out tracking isn't guaranteed. It depends on the hardware, the proprietary tracking software, the visual features in the environment, and even the motion dynamics.
Yeah.
For applications where even millimeter-level translation errors or degree-level orientation errors could impact analysis, such as clinical assessments, a rigorous calibration methodology is essential. A common strategy for characterizing tracking performance involves comparing the headset's pose stream against an external reference sensor, like an optical motion capture system. While effective, these approaches often require specialized infrastructure or introduce their own placement issues. This is where the work of Lopez Charbot and his colleagues comes in. They propose using industrial robots and collaborative manipulators
I
because
think.
the scope of their work is intentionally
Oh,
metrological.
1 minute.
To
1 minute.
propose using industrial robots and collaborative manipulators
Because they provide highly repeatable motion generation, making them an attractive reference platform for evaluating VR tracking under controlled trajectories. That's very cool. Highly repeatable motion generation, making them an attractive reference. What I can do, just repeat it.
effective, these approaches often require specialized infrastructure or introduce their own placement issues. This is where the work of Lopez Charbot and his colleagues comes in. They propose using industrial robots and collaborative manipulators Meta Quest 3 under controlled and reproducible conditions. The study is not about how the headset performs in dynamic, multi-axis, or visually degraded environments, but rather its fundamental tracking capabilities. So, how did they do it? The researchers developed a robot-driven calibration and accuracy assessment system. They rigidly mounted a Meta Quest 3 headset to the end effector of a TECHMAN TM5-900 collaborative robot using a custom 3D printed bracket. This robot boasts a certified repeatability of plus or minus 0.05 millimeters, making it an excellent, highly consistent motion reference. During data acquisition, the measurement conditions were kept stable, with ambient illumination monitored and maintained, and the visual scene unchanged for all trials. The robot then subjected the headset to precise single-axis movements. These included translational motions of 200 millimeters along the X, Y, and Z axes, and rotational motions of plus or minus 65 degrees for roll and plus or minus 85 degrees for pitch and yaw. Each test was repeated 3 times, and the resulting trajectories were averaged to improve statistical robustness. A crucial aspect of their setup involved data acquisition. Both the robot and the Meta Quest 3 streamed their position and orientation data to the same host computer. The headset streamed its data via UDP, while the robot, implemented as an ROS2 node, published its data to the same host. This configuration allowed for the simultaneous acquisition of both data streams, ensuring temporal consistency without the need for complex offline interpolation. Timestamps were assigned at the receiving application level using the host system clock, providing a shared time reference. To compare the data, all analyses were performed in a relative reference frame, effectively avoiding the complexities of absolute hand-eye calibration. This means they focused on how well the headset tracked movement relative to the robot's movement, rather than needing to know the exact absolute position of the headset in the world. Coordinate frame alignment was achieved using a technique called singular value decomposition,
SVD.
or SVD-based rigid body procrustes analysis. This sophisticated mathematical technique optimally aligns 2 sets of corresponding points. When we look at the results, the Meta Quest 3 demonstrated remarkable accuracy. Over 2,848 synchronized samples spanning 151 seconds, the headset achieved a mean translational root mean square error, or RMSE, of 0.346 millimeters, with a 3D RMSE of 0.612 millimeters. Its mean rotational RMSE was 0.143 degrees. Importantly, the Pearson correlation coefficients were greater than 9999 on all
On all
axes,
axes.
indicating an extremely high fidelity to the robot's movements. Let's break that down a bit more. For translational accuracy, the MetaQuest 3 achieved sub-millimeter RMSE on all three axes. The z-axis showed the lowest error at 0.261 millimeters, while the x-axis had the highest at 0.478 millimeters. The errors remained bounded within plus or minus 1 millimeter throughout all tests, with no systematic drift, meaning the headset's trace was virtually indistinguishable from the robot's. In terms of rotational accuracy, the pitch axis showed the lowest RMSE at 0.058 degrees, while the yaw axis exhibited the highest at 0.259 degrees. This higher error for yaw is consistent with the larger angular range tested for this axis and the known sensitivity of visual inertial slam to rotations around the vertical axis. Even with that, these are still extremely small errors, well within subdegree accuracy. The study also looked at cross-axis coupling, which refers to unintended movement along one axis when only another axis is commanded to move. This was minimal, ranging from
0,
0.044 to
0.7.
0.071 millimeters, indicating that the SVD-based alignment effectively decouples the Cartesian axes. Spectral analysis of the errors showed no narrowband peaks or dominant resonance lines, suggesting that residual errors are mainly broadband noise with limited low-frequency structures rather than strong oscillatory artifacts. What does this all mean? The level of tracking accuracy the researchers found is highly relevant for real-world applications. For context, conventional clinical tools for cervical range of motion measurements often have standard errors in the range of 3 to 5 degrees. The rotational errors observed here are substantially smaller than those clinical uncertainty ranges. These findings strongly support the MetaQuest 3's potential as a quantitative sensing platform for controlled rehabilitation-oriented applications.
Yeah.
Comparing this to other studies, the translational RMSE of 0.346 millimeters reported here is significantly lower than the 3.19 millimeters reported by Bonostrick et al. For the Quest 2 using realistic head trajectories on a different robot. This difference is expected because Lopez Charbao and his team used slow, single-axis, piecewise linear motions designed for controlled metrological characterization rather than naturalistic head motion. So, these results represent a best-case benchmark under very specific laboratory conditions. While impressive, it's important to acknowledge the study's limitations. The TECHMAN TM5-900 robot served as a repeatable trajectory generator, not a fully metrology-grade reference, meaning robot-related uncertainties are implicitly included in the error statistics. All analyses were also performed in a relative coordinate framework, so constant spatial offsets and residual frame misregistration were not explicitly quantified. The experimental protocol focused on single-axis, moderate-speed motions in a stable laboratory scene. Performance in more demanding settings, such as highly dynamic motions, complex multi-axis paths, or degraded visual environments, may show larger errors. Furthermore, the evaluation considered a single headset unit, a single robot, and one specific mounting configuration. Device-to-device variability or alternative setups weren't explored. Finally, while the tightly integrated acquisition pipeline reduced temporal misalignment, residual timing uncertainty due to communication delays and software scheduling can't be fully excluded. In conclusion, this work by Josep Lopez and his colleagues provides a robust, robot-driven protocol for quantifying the 6-DoF tracking accuracy of the Meta Quest 3 headset. Their findings demonstrate that, under controlled conditions, the Meta Quest 3 offers sub-millimeter positional tracking and sub-degree rotational tracking. This level of precision is highly promising for applications requiring accurate pose estimation in laboratory settings. These results establish a reproducible benchmark, though application-specific validation remains necessary before broader clinical or industrial adoption. If you found this information valuable, consider sharing this episode with someone who might also learn from it.
Okay, thank you so much for listening this podcast on this research paper. Okay, now I'm going to end this video. It's a lot for today. So the paper is ended. Okay, it's time to take a goodbye from you. Thank you so much for listening the podcast, reading the paper with me. Okay, and if you have read watch that video fully. So please don't forget to subscribe my channel and share with your all friends. Okay, thank you so much.